Hi everyone, my name is Andrea Barberio. I am a production engineer at Facebook, where I've been working for the past 5 years. I currently work on open source firmware, and here is my colleague Marco.
Hi, I'm Marco. I also work at Facebook. I've been there for 3 years now. I work mostly on open source firmware and platform security.
And today we will talk about how we are testing open source firmware at Facebook. So we will cover the problem statement, then we will talk about what our requirements are to test open source firmware internally. Then we will discuss the solution that we are pursuing, and Marco eventually will guide you through the architecture of the testing systems we are using. Let's start from the problem statement. Currently, we run open system firmware in production, as you can read in the link at the bottom of the slide about our F16 Minipack platform. We are treating firmware as software using an iterative development approach, as you can see from the bullet points. And today we will focus on the integration and end-to-end test part. For OSF, our development timeline is split into two parts, an external one and an internal one. The external one looks like this. You make a code change, you build it and run it, run your tests, and then run integration and end-to-end tests. Then you put up the code for review, where a human will review it, and if everything goes well, the code is merged. The internal process on our side is similar, and it looks like what you see at the bottom of the slide. After the code is merged externally, we import it in our internal repositories. Then we test them as shown above, and if everything looks good, we cut a release candidate. The release candidate will run on a limited number of selected hosts as part of a canary deployment, and if everything looks good, this will become a new release. So why do we need to test our open source firmware at all? With software, this is pretty obvious, and since we treat firmware as software, why shouldn't this be obvious here too? So system firmware is one of the most fundamental pieces of code that runs on our hardware, and as such, any bug can have a significant impact on performance, on security, on reliability. So we need to make sure that none of this ever become an issue. At scale, everything is amplified, and so even small issues can have a large impact on our operations. And for all of these reasons, we need a robust testing story for firmware too. In order to test our firmware properly, we had to lay down a set of requirements first. We wanted this testing system to be robust in order to minimize failures in prod and to detect errors early. We wanted it to be generic, so it can run in different infrastructure that can go from a small home lab to Facebook's data center infrastructure. This is important and will simplify also upstream testing. We wanted it to be scalable because in case it may have to deal with a large number of devices under test, and it must be simple by design so that everyone can easily approach it and can be productive both as a user and as a developer. We want it also to be flexible because we want to design with the reusable blocks that can be combined together to implement different operations. We have additional requirements, more human-related. We also want this testing system to be easy and set up to maintain, possibly as compact as having just a single binary to run on server side. It has to be easy to use so that our users can focus on the business logic rather than the code. For this, we want jobs and test steps to be expressed with configuration rather than with code. Of course, we want all of this to be open source, so everyone can benefit from our work, and we can collaborate together, and other people can integrate this testing system in their infrastructure. And of course, it must work with OSF, which is the primary goal for this testing system. So we looked for existing test systems, but none of them covered all of our requirements. Some systems were less flexible than we desired. Some systems were more complex to maintain and keep up to date than we wanted. Some systems had an architecture that would not work with our data center environment. And some other systems eventually had a model where all the tests will run and be controlled by the DUT, leaving no space for external orchestration. For this and all the reasons I discussed above, we eventually decided to go with a new system to help us with the automation of this task. And we call it Contest, which stands for continuous testing. Contest has a client-server architecture with a simple API. It's entirely contained in a single binary and it uses an SQL database, so it can be easily deployed. We even offer a Docker file to simplify this process. It's written entirely in Go, a language that we found to be very easy to learn and to use, and that provides some strong safety guarantees. Go is also the language used for root, so the Linux boot will be already familiar with it. Since one of our goals was to make this system generic, it can do much beyond firmware testing, and you can find more information about it at the link provided at the bottom of the slide. So let's see how do we describe jobs with Contest. In the slide, you can see a snippet of a job descriptor. A job descriptor is a piece of JSON that contains all the information we need to run a job. As you can see, you can define a job name, how many times it will run, how much time to wait between each run, if you want to run it, for example, more than once. Then you can see two sections with an ellipsis, test descriptors and reporting, that I will expand in the next slides. A test descriptor defines the necessary information to run a test. We need to know how to retrieve the list of devices under test and what exact steps we want to run on those devices. As I said, Contest is heavily modular, and all of these operations are implemented as plugins. As you can see, we need a target manager plugin and a test fetcher plugin. Those plugins are identified by their name and they are parameterized. In the example, the target manager is called the URI and it receives an HTTP URL as its parameter. The URI plugin will download the content pointed by that URL, which will contain the list of devices under test identified by their name and their ID. Similarly, at the bottom, the test fetcher defines how to retrieve the test steps. They can be either specified in line or can be downloaded from a central repository. In the example, you can see two steps that will execute two commands over SSH, sequentially and on each DUT in parallel, using jump.example.org as a jump host. So reporting is the final phase of a test. Reporting collects the results of the test and reports them wherever we desire. For example, it could be via email, it could be via instant message or a task. Since it's all implemented by plugins, you can also implement specific logic for your own internal reporting systems. Reporting is also modular, and just like the test fetchers, you need a plugin name and to pass some parameters to it. There are two types of reporters, run reporters and final reporters, as you can see from the slide. The run reporters are executed at the end of each test run, and they are provided with the data of each individual run. Final reporters instead are executed at the end of the whole job, for example, for a job that runs the same test 10 times. The final report will have access to the results of all the runs within the same job. There can be also more than one run reports or final reports. For example, you may want to report that at least 90% of your devices under test finished successfully, and you may also want to report for each run whether there were performance regressions. Multi-report reporters can help you do that. My part is over. Marco is now gonna give you more details about the architecture of Contest.
So when going through Contest architecture, it's always important to keep in mind that there are two different types of components in Contest. Those that can be swapped at runtime, and instead those that are fixed, so that constitute the core framework. Now you'll see both in this architecture diagram, and you will see the swappable ones in light colors and the core framework in dark colors. The entry point of a job in Contest is, as Andrea explained, a job descriptor, which is the JSON document that you have already seen. And the JSON description is submitted by a listener, which is a plugin implementing an interface that might be relevant for your infrastructure. So you might want to implement an HTTPS interface or Thrift or gRPC. Once the job descriptor is submitted, it's taken in charge by some glue logic, which is the API, context API component, and forwarded to the job manager, which is where the request is stored, persisted, and basically taken in charge. Now, every part of the framework has access to a storage layer that you can see at the bottom of the diagram. And this storage layer is roughly divided into two parts. The job API, which allows to persist changes in state for a specific job, and the events API. The events API allows to emit events, which are text description of something happening at a certain point in time. And these events are identified with names and payloads. The events are useful so that when something relevant happens, you can mark this point in time and you can go back later, for example, when calculating a report, fetch these events and calculate aggregates or metrics over all these events. We'll see later how the tester can use events via the API. So the job has been taken in charge, and now the job manager will orchestrate it through the various stages of its life cycle. The first stage is the acquisition of the targets. Andrea has shown an example of a target manager description before. And here, of course, it's pluggable logic. You might want to interface with any asset management system that is relevant in your infrastructure. And on top of the target acquisition, there's also the concept of target locking, so that multiple contest workers do not race for the same devices. Once the targets are acquired, we will acquire a test definition. And we have seen that it might be embedded into the job description, or it might be fed from another backend, a database, or anything that, again, might be supported by your infra. With a description of the test and the devices on which we want to run this test, we can start the actual sequence of tests. So the runner is the main scheduler that will orchestrate all the devices throughout the test steps, which are laid down in a pipeline fashion. And as Andrea mentioned, all the devices will go through each test step in parallel, in sequential manner. Once the targets complete the pipeline, the final phase is the reporting. The reporting, as Andrea mentioned, will calculate a JSON document that describes how your test performed. Now, we have seen that we might have different reporters and there's different type of reporters. And as a matter of fact, contest doesn't even have the concept of overall success rate. So every single reporter, depending on its logic, decides if a job is successful or not. So you might have the reporter that calculates reboot times and tries to see if there's a regression in reboot times, and it might decide that the job was successful. While another reporter, according to different criteria, might instead flag the job as failed. And here is also the point in time where you might want to go back and fetch all the events that have been emitted during the test and aggregate the metrics over all those events. As a developer, you will see most of the variety in terms of implementations in the test step, which are the plugins that do actions on the devices that actually carry out the testing logic. So it is worth zooming in a bit into the test runner to see what is required to implement a test step plugin. Next slide. So zooming into the test runner, you will see that each test step is associated with a control block. The control block is part of the core framework and is responsible for orchestrating the targets into the test step and out of the test step. It has responsibilities like making sure that all the input targets are accepted within a certain amount of time, that all the input targets actually are returned at some point in time and are not black holed, for example, by the test step. And it also makes sure that this happens within a certain amount of time, and then it evaluates the return values of the test step. During the execution, the test step has access to the events interface that we have seen is useful to mark specific point in time where relevant events happened. And this schema is replicated for every step which is part of the pipeline. And the runner will orchestrate via the control blocks all the targets through the pipeline. Now, all this enforcing, this example of the control block is the most relevant, but everything that is implemented as a plugin has a contract and also needs to implement a specific API. So it is possible to enforce contracts because most of the framework is programmed against interfaces, as we'll see in the next slide. So programming to an interface means that the plugins must adhere to a specific contract in terms of how channels, for example, should be used for I/O, which return values make sense, which timeouts should be enforced. And we have seen the example of the test step, but the same concept applies to target manager or test fetcher. And contest is designed so that the moment the API and the contract is not respected, the whole job is terminated. So a cancellation signal is propagated to the whole job. And the specific subset which created the issue is flagged to be inspected later. The interfaces are also designed in a way so that early validation of the parameters is possible. Andrea mentioned one of the principles behind contest is that it has to be robust. So as much as possible needs to be caught at compile time possible. But if not, then as early as possible during job submission. So we have seen that the plugins accept parameters, but there's no guarantee that those parameters will be meaningful or can be consumed later when the job runs. So we ask each plugin to implement a function that will say very early when the job is submitted if the parameters are correct, if everything can be consumed later on. So we wanted to reject the submission if there's anything that we think might result in a failure later on. And all this logic that validates the various APIs and contracts is implemented by the core framework. And it's extremely important that it works and is not subject to regressions. So what we can do and what we do is implement integration tests that operate on plugins that have bugs, for example, that misbehave. It could be a plugin that panics in the middle of the execution, or a plugin that times out, or swallows and black holes target. Now, these integration tests make sure that the core logic in the framework that detects these misbehaviors correctly flags them and terminates the job, so that we can make sure that the life of the developer is as easy as possible, and any bug that might slip through is detected and flagged immediately. This is an overview of the architecture. In the next slide, you will see how you can look into the code. You can contribute if you're interested. So next slide. Obviously, you're welcome to contribute, and we are looking for contributions and to develop and deploy contests where it can help validate hardware or firmware. And you can clearly get in touch with us directly by email, or open pull request, or issue directly on GitHub. With this, we have concluded. If you have a question, we are happy to take any question.
Thanks, everyone.
Oh, hello, everybody. We are here to take questions. There was just one question from Peter that was already answered in the Q&A section. If there's no further question, I think we can just wrap up.
Yeah. Thank you, guys. Thanks so much.
Thank you very much.